In section 5.8, we're looking at solving equations involving a radical expression, and that's our primary objective. We're going to use algebraic and graphical approaches. Okay, so we're doing that dropping things out of the sky model again that we used in the last section with that square root of d over 4 or 1/4 square root of d. Okay. The first question that they ask us to do is figure out how far it's going to, or how long, sorry, in the answer to time, is going to take for an object to fall a distance of 1,450 feet. So we're going to take our function t, and we're going to plug in 1,450 feet. So t equals the square root of 1,450 divided by 4, which comes out as 9.52 seconds. Round to the nearest hundredth of a second, so 2 places as I have done. Okay, complete the following table round to the nearest hundredth as well. So I already typed my table in to save me some time. And you can see that as you have a longer distance to fall, the amount of time that you fall increases. It does increase more and more slowly because this function is a slow growth function. It increases more rapidly at the beginning and increases less and less over time. It's not the slowest possible growth. Logarithmic functions win that. They're the slowest possible growth functions, but they kind of have some similarities in the shapes of their graphs. So this is our squared graph function. It does increase at a decreasing rate. All right. How tall must the building be for the object to take 6 seconds to fall to the ground? Use my graph to answer. Okay, so if I'm going to use my graph to answer, then I need my output time to be 6 seconds. So we'll do y equals 6 here. And it would need to be 576 feet tall. Okay, so if the building was 576 feet tall, it would take 6 seconds to hit the ground. So we solved that graphically. What they'd like us to do next is to work on solving that algebraically. Okay, so moving decimals out of the way, as they say here at the bottom of the page, an equation where there is a radical on at least one side is a radical equation. This equation is a radical equation because there's a square root on at least one side. Cool. Okay, then they're also saying that if I'm going to solve something by hand, it's okay to raise both sides to the same power. So in my square root case, I could take the opposite of a square root, which is a square, and square both sides, and I'd be able to use that property to solve. So we're going to solve this equation by squaring both sides. Okay. Now, when I square both sides, I need to square everything on this side, the d squared and the 4. So this is going to give me, first of all, t squared equals d over 16. Now, you actually had some options here. You could have multiplied the 4 over first or squared both sides first. It really depends on what the number is, what is easier to do. But I have to get that 16 to the other side eventually. So we'll multiply both sides by 16 next. And so that's going to give us a simplified version of 16t squared equals d. So the new formula helps us determine how tall a building must be. I would just take 6 seconds. Use the same formula. Okay, so 16 times 6 squared equals d. So this means that if I just plug in 16 times 6 squared, I also get 576 feet. How do my answers compare? They're the same. Okay, how could we also answer this equation by solving this by hand? Okay, so we solved the equation by Reordering it, now we're going to solve the original equation algebraically with the number 6 in place. So for a little variety, perhaps we would multiply the 4 over first and get 4 times 6 is 24 equals the square root of d, and then maybe we would square both sides. So what is 24 squared? I can't type. There we go. 576. So that's another way to have solved this one. So this would have been the by hand algebraic way to solve the original equation that we were posed with. We solved graphically first, right? We graphically solved this and got our 576, but algebraically I would have solved it by squaring both sides, multiplying that 4 over in either order. If you square both sides first, you would have had 16 to multiply over, of course, or you multiply over first and then square both sides. Okay. Okay, so we're going to look at doing this process in a few more instances. Let me move decimals out of the way. There is a lovely example here of squaring something and solving. If you check out example 3, we're going to do this with some marbles falling. Okay, so suppose that two different objects are dropped. We got a marble and a beach ball. Because of air resistance, the beach ball is going to take longer to fall than the marble, and assume that the marble falls according to the original 1/4 of square root of d, same as in the problem above. The beach ball is going to fall with a different rate. It's going to have a different constant of proportionality. This is a direct variation case where k is that constant of variation or constant of proportionality. And I don't know what k is yet. So we got to do some work to find k first. Okay, so in the beach ball case, if the beach ball is dropped from a height of 250 feet, it takes 4.11 seconds to hit the ground. Determine k. So the time is 4.11 equals k times the square root of d, and the distance is 250 feet. I'm not solving for the thing under the radical, so I'm not squaring both sides. I'm just going to divide this number off. So we're going to save this property for later. I don't need it right now. It's kind of in the wrong spot. I'm not trying to get a variable inside the square root by itself. So I just need to divide both sides by the square root of 250. So divide both sides by the square root of 250. That's going to get k by itself. So I'm going to take, just clear this thing. I'm going to take 4.11, I'm going to divide it by the square root of 250 and round to the hundredths place. That gives me 0.26 for k, 0.2599 or 0.26 for k. Okay, so they confirm that in our beach ball case, we're going to use 0.26 for our k. Now, they also say that we're going to drop the beach ball from 50 feet lower. We're going to give it a head start because it's going to fall slower. Give it a head start. So that's going to be the equation d minus 50 to give it that 50-foot head start for a beach ball. All right. Write the equation that can be used to determine from what height the marble must be dropped so the marble and the beach ball hit the ground at the same time. Okay, so the marbles equation was 0.25 square root of d, and I want the beach ball to hit the ground at the same time, so I want my 0.26 square root of d minus 50 to be equal to it. So I'm going to set these two equal to each other, and we're going to solve this using the algebraic approach. All right, which means square both sides to start getting rid of your square roots. If there was only one square root, perhaps I would divide one of these numbers off from the other. But with those itty bitty numbers, it's probably best to square first. And I've got two square roots anyway, so we're going to square both sides. Okay, so I need to figure out what 0.25 squared is. And I got to write down a bunch of places on this. So 0.0625. And then when you square the square root of d, you get just regular d. And then I want to figure out what 0.26 squared is. That's 0.0676. Then when I square the square root of d minus 50, that gives me the quantity d minus 50. and then this value would distribute. Okay, so 0.0625D equals 0.0676D minus, I'm distributing this to the 50, so we need to take this number times 50. That's going to give me 3.38. And then I want to subtract and get these two values on the same side. So we're going to subtract the 0.0676D. Okay, so I need 0.0625 minus 0.0676. That gives me negative 0.0051D equals negative 3.38, and divide both sides by negative 0.0051. All right. And that gives me negative 3.38 divided by negative 0.0051 gives me 662. I should have typed another negative here. I just forgot. There we go. Gives me 662.75. Okay, so we're at my conclusion on the other side. So if we drop the marble from 662.75 feet and the beach ball from 50 feet less, so from 612.75 feet, they'll hit the ground at the same time. Okay, and then they want us to solve this graphically as well. Okay, so if I want to solve this graphically, we're going to graph the right-hand side and the left-hand side of the original. So y equals 0.25 square root of d, and y equals 0.26 times the square root of d minus 50. Now, if I didn't already know what the answer was, I might have trouble rescaling my graph. I am going to make sure that my input value is bigger than 662. So I'm going to make it, say, 800. And let's see if we can see the intersection point. There it is. At 662.745 or 662.75, they will both hit the ground. And coincidentally, it's going to take them, the output there of 6.436, it means it takes them, that is the time, it takes them 6.436 seconds, I believe. The units on here are seconds, to hit the ground. I'm just checking that they're seconds. Yes, they're seconds. So just for fun, we'll note that as well down here. After 6.436 seconds. And I could have gotten that value algebraically had we chosen to by plugging the D value, 662.75, into the equation for D in either equation. I would have come up with a 6.436. All right, on to the next example. Consider this scenario. So we have our equation, we subtracted 5 from both sides, we squared both sides, we subtracted the 3 over, and we got x equals 22. It appears to be the solution. Check it. Does it work? All right, so in the original, if I have the square root of 22 plus 3 plus 5 equals 0, that's the square root of 25, plus 5 equals 0, that's 5 plus 5 equals 0, and that's no, not true. And so when this happens, the solution is going to be extraneous. And one of the reasons that this is extraneous is actually we can see where it broke down. It broke down right here because the range of the square root function is y greater or equal to 0. And so when you had a negative value being equal to the square root function, you're like, that can't happen. And so you knew that any solution that resulted from it was going to be extraneous. They're not always quite so obvious though, so it's really important to check that your answer is going to be true because there are occasionally extraneous solutions. Okay, so that's what happened in the process to cause that extraneous solution is we had the square root equal to a negative value. So does this have a solution? The solution is not 22, but does it have a solution? Okay, use a graph to verify our solution. And the equation that I want to be equal to 0 is y equals the square root of x plus 3 plus 5. Yeah, it doesn't touch 0. It's starting up high. It's never going down to 0, so there is no solution. So there is no solution. That should be 2 words that kind of got smushed together when I was writing. It has no solution because the graph never crosses the x-axis. All right. In the last question, what they would like us to do is check this data in this model and see if it's a good one. Okay, so I got my data typed in over here. I hope it's typed right. Let's check it out. 0, 4.2, 4.5, 5, looking good. Okay, and they want us to check out this model and see if it fits the data. So n of x equals 1.222 times the square root of x plus 0.24 plus 3.442. Well, I don't think I've ever looked at this function before, but it does not seem to be doing a particularly good job of modeling this data. So this data was modeled by this function. I would say this function is probably not really a good estimate for this data. It's a little too high. They're going to ask me to use it, but then I'm going to talk about maybe how to get a better model for this data. So we'll use it because they've asked us for the time being, and we'll come back to this. I don't think I've actually graphed that model before. It's not as good as I was hoping. Okay, so determine the year that this model, bad or not, would predict the number of undergraduate students receiving Stanford loans to be approximately 8 million. So 8 millions are out, but our outputs are in millions. So we're going to plug in 8 equals our 1.222 times the square root of x plus 0.24 plus 3.442. Okay, so when I want to solve this, I got to get my square root term by itself. So I absolutely must subtract off this 3.442 first. I got to get rid of that term because it is not part of the square root term. Get rid of it. All right, I'm going to have my function up here just for some work on this. 8 minus 3.442 is going to give us 4.558 equals 1.222 times the square root of x plus 0.24. Now, I think the next thing I would like to do is to divide off this 1.222 because I don't want to square like both of those numbers and get 2 nasty numbers. Why don't I just get 1 since they're already kind of messy as it is and then square that result? So 4.558 divided by 1.222 would give us 3.72. I'm going to keep a few places on it because those 9 nines, 72995. That's Otherwise, I'd have to round it to 7.3, and that only has 2 places, so let's just keep a couple extra. And then equals our square root of x plus 0.24. All right, now we're ready for the step when we are trying to get rid of the square root, so we square both sides. So I'm just going to drop in some parentheses here so that I can square this and then not have to retype everything. Sounds good to me. So I get 13.913 equals x plus 0.24. And then I'm going to have to subtract that 0.24. It's kind of blurry there. There we go, 0.24 from both sides. Got the number there, so I'm just going to minus 0.24. And I get 13.673 equals x. Okay, there we go. So it looks like it's going to take about, are these years since anything? Yeah. So it's going to take about 13.6 or about 14 years for there to be 8 million student loans. So after 13.67 years, or if you want, you can round it to approximately 14 years, there will be 8 million Stafford loans. Okay, that is the end of this section. Now, I mentioned fixing this model. So I didn't like it when I saw it, and I was like, we could do better. And so I wanted to just do a regression on this model of the same form and just see if I can get it to look a little better. So this model had a coefficient, a summary value, and an additive at the end. So I'm going to call these A, B, and C. So I would do a y1 approximately a square root of x1 plus b, plus outside the particle, plus c, and see if that was any better for the model. So if I compare those two, the first model is just like it's all high, right? And then the second one, this model, this data, it's not perfect, but the r squared on the second one has a 0.97. And so we're able to get a teeny bit closer. And what's just a little bit better about this data, this model compared to the data than the first one, is that it goes to the middle of the data. Some of the points are high, but some of them are low. Whereas really here, they're almost all too low. So the model is too high. So there is this one point above it, but everything else is below it. So I didn't like the green model. This would be another model using regression. They must have used some other method to come up with this equation. I just wanted to mention it. I could do regression of any form. I want to, if I know what I want the equation to look like, we can do a regression on the equation, on the data.